In the last few videos, we've made a few bits of our cluster computer that we're calling the chatter. What bits did we make then? So, we made this bit here, that's a pattern matcher. This bit over here, that's the inbound buffer, and this little flip-flop thingy down here. But before we stick the bits we already made together, let's make another bit, because when we made the pattern matcher, we just tested it by plugging a bunch of wires in. But what we really need to do is make these bits here. This is the physical address of the board, this is the pattern register, and this bit here is the don't care register. So, let's make that on a breadboard. So, human man, get that breadboard. Now, get that 8-way dip switch over there. Now, stick it on the board. This switch will give the physical address of the computer. Stick the chips on there, human man. Get them resistor arrays over there. Yeah, well, you've got to stick one on the switch and your human man, like on the schematic. There you go. Now, stick the other one on the don't care register's output. Now connect it all up, human man. Human man, connect up that address board thing you just made. Yeah, that. Connect that up to the pattern matcher. Yeah, well, human man, you've got to stick some wires on there and all, ain't you? Yeah. What we're going to do is cut the camera, the human man's going to do the wiring, and then we'll come back when he's done. Because, you know, watching someone bunging a bunch of wires on a breadboard, that's boring, isn't it? Looks like the human man's finished. Alright, human man, you stick that flip-flop thingy we made last time on there. Yeah, that thing there, human man. There you go, human man. Now tidy them wires up a bit. Yeah, them ones there. So let's come back once the human man has done some tidying up. Okay, human man. Stick some more chips on there. Oh yeah, well, before the human man goes sticking a bunch of random chips on there, I suppose we better go through all that decoding lark we talked about at the end of the last video, haven't we? Right, so, let's have a look at the paper. Yeah, this paper here, the one we've been looking at the whole time. Right, now, let's look at the control register. In particular, these last two bits here, AD and DM. AD stands for all destinations, and DM stands for destination mode. And look, they've given us a little table here telling you what each one does. Isn't that nice of them? You can read that in your own time. There's a link to this paper in the description. What we're going to do is go to the schematic and go through how the circuit works. The main bit of the circuit is this bit here in the middle. That is a 74HC139. Which is a 2 to 4 decoder. The first scenario we're going to have a look at is this one here. That DM is 0 and AD is 0. And when they're both 0, this output here is a 0, and all the other outputs are 1s. And when we have a 0 on this output, well, that puts a 0 on the chip enable pin on this 748C245, which puts the address on the A input of our pattern matcher. And then on the B input, we have the destination. Now, when the address doesn't match the destination, we get a 0 on this output here. And when the address does match the destination, we get a 1 on this output. And we're going to use that later on. So the second scenario we're going to have a look at is when DM is a 1 and AD is a 0. That puts a 0 on the second output of the decoder, which puts a 0 on the output of the pattern register and the don't care register. So the pattern is on the A input of our pattern matcher and the destination is on the B input of the pattern matcher, just like before. And just like before, when they don't match, we get a 0 on this output, and when they do match, we get a 1 on this output. And as before, we'll use this later on. The third scenario is when AD is a 1 and DM is a 0. And that puts a 0 on the third output of the decoder. And what that does is puts a 0 on the input of this NAND gate, which puts a 1 on the output, ignoring anything that's happening with the pattern matcher. One thing we ain't mentioned yet is the BF flag. That's also part of the control register. What that stands for is bin full. So when it's a 1, that means the message is all new and fresh, ready to be read. And when it's a 0, that means it's a horrible old stale message and you don't want to read it again. But when AD is a 1, it keeps the message fresh, so all the processors can have a look. So in the final scenario of our combination of AD and DM, that's AD is 1 and DM is 1, well, that does the same thing as our second scenario, where we use the pattern register, but this computer doesn't consume the message. So another computer can then read it as well. So the BF flag and the output of the NAND gate both go into the inputs on this AND gate. Well, what are we going to do with the output of this? Because we saw this last time, didn't we? And it weren't connected. What are we going to connect it to? What we're going to do is stick this in the D input on the D-type flip-flop we stuck on there last time. So if either the output of the NAND gate or BF are 0, well, the inbound buffer don't get clocked. So the message don't get loaded onto the inbound buffer. Right, let's get back to building it. You get that 4 input AND gate and stick that on there first. Next, stick the old decoder on there, human man. You'll have to take that LED out of the way, wouldn't you? And now finally, the 3 input NAND gate. Where are you going to put that then? I suppose you better wire it all up, ain't you, human man? Right, so the human man's finished that circuit, so let's test it. Well, we'll point to some bits, human man. So, the address is this bit here. Well, you've got to point to it, human man, when I say it. Yeah, that's it, human man. The pattern register is this bit here. Point, human man. And the don't care register is that bit there. Yep, human man. You got a point again. Yep. So, Try changing the address, human man. Oh look, the pattern match has gone off. Now, clock the flip-flop. Yeah, that thing there. And look at that, the light's gone out. Now I'll change the address back to what it was. And clock. Oh, look at that. Now, emulate a read. Look at that, human man. Now you've got to test the pattern bits, haven't you? So to do that, the human man has got to load those two registers down there. Point to them, human man. Yep, that's it, human man. So, seeing as everything's just tied to ground at the moment, you might as well load the don't care register first. Yeah. Well, actually, human man, you shouldn't have done that, should you? What you should have actually have done was loaded the pattern register. Yeah. Now you make them all ones, and then you load the don't care register. Now you've got to change the mode so it uses patterns. Change that yellow wire there, human man. Yeah. Now, try changing the destination, which we're emulating with them wires over there. And there you go. Now, human man, load the don't care on bit 0. And look at that, human man! It's working! Ooh! Well, isn't that exciting, human man? Now, the human man has got a bit carried away, and he's connected up the ring bus to the inbound buffer. The ring bus is on the left, and the inbound buffer is on the right. And all he's done is connected all the outputs of the 74HC574s on the left hand side to all the inputs of the 74HC574s. And then he's connected all the outputs of the inbound buffer together. And that's it. Now the human man just needs to attach that bit to the bit we just tested. So, there we go. The human man, he's wired it all up. And now, I suppose he better test it, innit he? Wait, human man, you added an extra bit, didn't you? You added that hex inverter. Well, you've got to point to it, human man, otherwise they won't know where it is. Yep, that's it, human man. So what this does is inverts the shift clock of the ring bus. Which is what we use to clock the flip-flop. Well, I suppose the only thing you've got left to do now, human man, is switch it on and test it. So, human man, try starting it off by reading data register 1. And look at that, human man. The LED's gone off. Now, clock the ring bus. Oh, the LED's come back on. Try setting BF to 0. Now clock it again. Oh, it's gone off like it's meant to. Now put BF back to 1. Now clock it again. It's gone back on. Now try changing the destination. And clock it again. Ooh, it's gone off. Well, I suppose we better try some of these other functions, ain't we? Try DM is a 1. That should make it use the pattern register and the don't care register. So before the human man clocks the ring bus, he should probably load the pattern register and the don't care register. Go on, human man, you do that. Load the pattern register with all zeros. Well, seeing as all the jumpers are actually on 1s, probably be easier if you just load the don't care register first. There you go. Now stick them all on zeros and load the pattern register. Right, now clock the ring bus. And there we go, exactly the same. But if the human man changes the address, it don't do nothing. Ooh. So change the destination, human man. And look, it's gone off. Right, now load the don't care register with a 0 on the first bit. Look at that, human man. Almost like we know what we're doing. Except we don't. And we can prove that by having a look at this bit of the schematic here. Can you see what the problem is? That's right. When it's in all destinations mode, that is when AD is a 1 and DM is a 0, well, you see, what happens is the physical address of the board and the pattern register, well, they both turn into big floaters, which means the input of our pattern matcher is also a massive floater, which is bad. But we can fix that by sticking a network resistor in there. So, human man, you stick that network resistor on there as a pull-up. There you go, human man. Now connect the other end to power. So now, when the human man puts it in all destinations, it won't be floating. Because we don't like floaters, do we? So try that, human man. It works, human man! Human man! It all works! Whoa! Right, well, I suppose that's another video done. We're starting to make some proper progress now, aren't we? Won't be too long till we're doing some computerising, will it? That reminds me, how's that human man getting on with his studying? You mean you've only got to chapter 4, human man? You got loads more to do after that. Don't forget, that's only an introductory book. Yeah, you got way more complicated stuff after that. Yeah, you better get your finger out, ain't you, human man? Next time, we'll, well, I don't know yet. We'll probably just make some more of it, won't we? It's what we've been doing, isn't it? So, yeah, I'm going now. Roll, 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 roll! Bog! Let us watch as Jeff flies majestically in his portable toilet, propelled by nothing less than his own torrential diarrhea.